Hi guys, welcome to Basic Semiconductor Materials, the first video or presentation for Electronics 1, your introductory course to electronics for those at college or university. Your presenter is Motion Marufu, and for any comments or suggestion, don't hesitate. And I am on motionmarufu68gmail.com or on WhatsApp +2637175358666. Enjoy this one. First things first, objectives. By the end of the presentation, you guys should be able to distinguish a semiconductor from a conductor and also from an insulator. You must also be able to state the commonly used semiconductors and their characteristics. Then, using a Bohr model, you must be able to describe silicon germanium atoms. Last but not least, you must be able to analyze the properties of silicon as well as those of germanium. From our high school, we are familiar with conductors and insulators, and even examples of conductors as well as examples of insulators. A recap: a conductor is the material that allows electricity to pass through it, while an insulator is a material that does not allow electricity to pass through it. This is what we learned at high school. Examples of conductors are silver, copper, and aluminium, while examples of insulators are plastic, rubber, wood, paper, to name but just a few. And we know that the wires that bring electricity to our schools or to our houses are made of conductors, and the mostly used is copper, followed by aluminium. The wires in our houses are insulated by polythene. Why? To avoid short circuits. So we find an application of insulators. There is another material whose conductivity lies between that of a good insulator and a good conductor. That material is a semiconductor. In other words, a semiconductor is a material that conducts less than a conductor but more than an insulator. That is to say, its resistance is more than that of a conductor but less than that of an insulator. Example of elements that are used to make semiconductor devices are germanium and silicon. So we can say basically electronics is the start of semiconductor theory. A look at the three materials in more detail. Conductors. These are substances or materials whose conductivity is very high at normal temperature. What do you mean by normal temperature? We'll normally be referring to room temperature. This means that the atoms of a conductor can easily be released from the valence shell into the conduction band to become free and contribute to electric current flow. Don't worry, we'll look more into some of the terms in that statement. Then, what is an insulator? These are substances or materials whose conductivity is very low at normal temperature or at room temperature. That is, they do not allow electricity to pass through them easily. It means that the atoms of an insulator cannot easily be released from the valence band into the conduction band to become free electrons. Then semiconductors. These are materials whose conductivity lies between that of a conductor and an insulator, and to expound on that, they conduct less than a conductor but more than an insulator. Conductivity and resistivity of the three materials, conductors, insulators, as well as semiconductors. We've got a table to that effect: materials, conductivity, resistivity, and then the classification. So the classification is being done not according to names but according to conductivity and resistivity. Silver is the best conductor, having a conductivity of 6.25 times 10 to the power 7, followed by copper 5.88 times 10 to the power 7. You can see that this is higher than this. And aluminium in the third position with a conductivity of 3.85 times 10 to the power 7. Silver is the least resistivity, 1.6 times 10 to the power 8, followed by copper 1.7 and aluminium 2.6 times 10 to the power minus 7. This is the reason why these materials are classified as conductors. Why? Because they allow electricity to pass through them easily. Germanium and silicon, we've said they are the two commonly used semiconductors, and silicon being widely used when compared to germanium. And please take note, these haven't been doped. They are said to be pure. Germanium, a conductivity of 1.4, which is far much higher than the conductivity of silicon, which is 5.0 times 10 to the power minus 4. Then if this is higher than this, then this ought to be lower than this, and this makes sense. Hence, the two are classified as semiconductors. These insulators, if we look at their resistivity, this is very, very high, even if you compare them with the conductors or even with insulators. Hence, they do not allow electricity to pass through them easily. Hence, they are classified as insulators. Insulator, insulator, and insulator. So this table is very, very important. We are now going to analyze conductors and semiconductors with reference to coefficient of resistance. And what are we saying? We are saying when we increase the temperature of a conductor, its resistance increases. So a conductor has got what we call a positive temperature coefficient of resistance due to that fact. A semiconductor has got a negative temperature coefficient resistance. And what does that mean? It means that if we increase the temperature of a semiconductor, its resistance decreases. In other words, it conducts more when we increase its temperature, while a conductor conducts less when we increase the temperature. A conductor, because it has got more electrons in the conduction band, if we increase its temperature, it means we are going to have more electrons escaping into the conduction band, such that the electrons will disturb each other insofar as their movement is concerned, and this results in its resistance increasing. How can we increase the conductivity of a semiconductor? We can improve its conductivity by adding some impurities, the process which we call doping. And what do we mean by impurities? We are simply saying we are adding some external atoms in a crystal of silicon or germanium, and those are going to provide electrons to the crystal of a semiconductor. So we have simply said the semiconductor has got a negative temperature coefficient, while a conductor has got a positive temperature coefficient. We are now going to look at the Bohr model, and the function of a Bohr model is to explain the structure of an atom. What is an atom? An atom is the smallest electrically neutral particle of an element, and we know that it can take part in a chemical reaction. An atom is made up of a nucleus and orbital shells that surround the nucleus. In the nucleus of an atom, or at the center of an atom, we find neutrons and protons. Neutrons have no charge. Protons have got a positive charge. These two do not move. Surrounding the nucleus, we find orbital shells, and they differ from atom to atom. And in the shells, that's where the electrons move around or revolve around, and electrons have got a negative charge. The electrons in the outermost shell are what we call the valence electrons, and these are the electrons that take part in a chemical reaction. Please take note. These are also the electrons that contribute to electron current flow or to electric current, in that they can escape from one atom to the other atom, or they can escape from the valence shell to the conduction band, and electrons move in the conduction band, contributing to electric current. That's basically what we mean by the Bohr model. This slide is very, very important. You must go through it apart from the video. Please take note that there's no difference between an electron in an atom of copper and an electron in an atom of aluminium, or an electron in any other element on the periodic table. And please take note that there's no difference between the behavior of a proton in any one atom and a proton in another atom of a different element. Please take note, those points are very, very important. The same applies to neutrons. They are not different. So, what are we saying? We are saying it is the difference in the number and arrangement of electrons, protons, and neutrons of each atom that matters. And we are now going deeper. We've got what we call the atomic number. The atomic number is the number of protons in an atom, or we can also say it is the number of electrons in an atom, and the two are the number of protons is equal to the number of protons is equal to the number of electrons. Hence, an atom is said to be neutral. The electrons reside in the orbital shells around the nucleus of an atom, and the number of electrons in a particular atom are deduced from the formula 2n squared. For example, the first shell n is equal to 1, so we are saying 2 times 1 is equal to 2, hence the first shell contains 2 electrons. And you deduce n according to the number of shells that a particular atom has. Because there are atoms with 2 shells only, atoms with 3 shells only, and also atoms with 4 shells, just like a copper atom. So you deduce the value of n from the number. Then we are now going to look at the periodic table. All the elements are arranged in a periodic table as shown in the next slide. And the group of a particular atom determines the number of electrons it has. We are now going to have a look at the periodic table, and that is just a part of the periodic table. We have got what we call elements. So we've got group 3 elements, group 4 elements, as well as group 5 elements. These are the groups that are important in electronics. Why? Because group 3 and group 4 elements are used to dope germanium or silicon to improve their conductivity. And examples of group 3 elements are boron, aluminium, gallium, and indium. And the number in brackets represent the atomic number or the number of electrons. Then group 4 elements shown, we've got carbon, silicon, and germanium. And in electronics, it is these two that are commonly used, with the silicon being the mostly used of the two. Then we've got group 5 elements, which are elements with 5 electrons in their valence shell. And shown is phosphorus, arsenic, and antimony. And phosphorus has got 15 electrons or 15 protons. Group 4 elements have got 4 electrons in their valence shell, while group 3 elements have got 3 electrons in their outermost shell. So these group elements are very, very important in electronics, and we'll cover them in detail in the next presentation. We now want to analyze the relationship between electrons in the valence shell and conductivity. I think you agree with me that atoms with less than 4 electrons in their valence shell are good conductors of electricity. For example, copper, aluminium, and silver, they are very good conductors of electricity. You'll also agree with me that atoms with more than 4 electrons in their valence shell are poor conductors of electricity. And atoms of interest, which we are discussing in this presentation, have got 4 electrons in their valence shell, and they are known as semiconductors. 4 is half of 8, which is the number that is needed for a particular atom to be stable, and the maximum number of electrons that it can accommodate in the valence shell. Atomic structure of some elements. We've got hydrogen atom, aluminium atom, silicon atom, phosphorus atom, as well as germanium atom. I will dwell much on semiconductors. The silicon atom has got 2 electrons in the outermost shell, 8 electrons in the valence shell, as well as 4 electrons 8 electrons in the next shell and 4 electrons in the valence shell. The same applies to germanium. It has got 2 electrons in the valence shell, in the next shell 8, and then in the last shell it has got 4 electrons. So as you can see, group 4 elements have got 4 electrons in their outermost shell, as you can see. Phosphorus will dwell much on the valence shell, which is the important shell. Phosphorus has got 5 electrons in the valence shell. Aluminium has got, it's a group 3 element. It has got 3 elements in the valence shell. Phosphorus, group 5 element, it has got 5 electrons in the valence shell. Group 4 elements have got 4 electrons in the valence shell. So that's basically what we are doing. We are simply analyzing the atomic structure of some elements. Why silicon is widely used when compared to germanium is what we want to look at right now. From the Bohr model, we saw that germanium has 4 shells, silicon has 3 shells. This means that the valence electrons of germanium are far away from the nucleus when compared to the valence electron of silicon. This means that they have more energy than those of silicon, which means that when we increase the temperature of the two materials, more electrons from germanium are going to jump the forbidden gap to contribute to electron current flow than those of silicon. This means that at high temperature, germanium is unstable when compared to silicon, and stability determines the quiescent point, which is the operating point of a semiconductor. So the instability of germanium at high temperature is not wanted. Hence, most semiconductor devices are manufactured from silicon, which is stable at high temperatures. Who doesn't want to get married to someone who is stable? We said an atom has got orbital shells around its nucleus, and in the orbital shells, that's where we find electrons. According to the number of shells, electrons in the innermost shells do not leave the atom, but it is the electrons in the outermost shell that, if they acquire energy, they escape to nearby atoms. It is these electrons that contribute to electric current. So electrons can, if they acquire energy, if they are excited, which is the term that is used, they acquire energy and escape from the valence band to the conduction band. When they are now in the conduction band, then they contribute to electric current flow. They are referred to as free electrons. It is due to the presence of these electrons in a material that it is able to conduct electric current. Electrons in the other inner shells are said to be bound electrons. Why? Because they are attracted to the nucleus and cannot escape. And for semiconductors, we know 4 electrons are found in the outermost shell. Electron energies. In this slide, we are trying to establish the relationship between orbital shells and energy levels. And this comes from modern physics, which states that we only have got discrete values of electron energies and not any other. That is to say, electrons cannot have any value of energy except the permissible ones. What we are simply saying is electrons exist in these shells, not between shells. And those shells have got energy levels associated with them. As I have said before, electrons in the valence shell have got the most energy when compared to electrons in the inner shells. So we now want to see the relationship between valence shells and energy levels. The slide is showing the relationship between energy level and the valence electrons. This is the Bohr model of a hydrogen atom. This is the nucleus. This is the first orbit shell, second orbit shell, and the third orbit shell. The energy of an electron in the third orbit shell corresponds to level n is equal to 3. the value of energy in the second orbit shell corresponds to n is equals to 2, and the amount or the level of energy in the first orbital shell, it corresponds to energy level n is equals to 1. The value of energy is increasing from the edge of the nucleus to this level. So we are saying from the nucleus, the amount of energy increases with distance from the nucleus. So valence electrons have most energy, followed by electrons in the third orbital shell, followed by electrons in the first orbital shell. So we are saying in between the orbital shells, no electrons resides. So we don't have electrons in this, and we also have electrons in between these two shells. And the electrons have got discrete energy levels or permissible energy levels. So no electron resides or has got any energy between the levels n is equals to 2 and n is equals to 3, and also between n is equals to 1 and n is equals to 2. So the relationship between orbital shells and the amount of energy. There is a relationship between atomic shells and electron energy. And what are we saying? We are saying the greater the distance of an electron is from the shell, the more the energy it contains. This means that electrons in the innermost shells have less energy when compared to electrons in the outermost shell. This means that when heat or light is applied to a particular atom, it is the electrons in the outermost shell that escape to nearby atoms. So we are saying is the further the electron is away from the nucleus, the more the energy it contains. Hence, it is the electrons in the outermost shell that normally become free and proceed from the valence shell to the conduction band. So this is the reason why it is electrons in the outermost shell that have got maximum energy or that take part in chemical reactions. Electrons in innermost shell do not define the chemical characteristics of a particular atom. So we are saying when light or heat impinges on an atom, the energies of the electrons increase, and as a result, they are lifted to higher energy levels. So when electrons are lifted to higher energy levels, we say they are excited, though it does not last long, because very soon they will fall back to their original energy level. We are now talking about a solid, and in a solid we talk of the energy bands because of the millions of electrons in a particular level or band. So we've got first, second, third, and the conduction band, which becomes our fourth band. But we are saying if we equate that to the energy levels or to the orbital shells around an atom, we are saying the first level is now the second band, second level is now the second band, and the third level is now the third band, and it is the valence band. So if electrons escape from the valence band, which is the third band, to the conduction band, they become free electrons, and they must acquire energy greater than Eg, which is the energy gap. It's otherwise they remain in the valence band because no electrons exist except at permissible energy levels. So in the energy gap, no electron exists. And we have also said electrons can fall back from the conduction to the third band or to the valence band if they lose energy. So that basically what the previous slide was saying, that we have evolved from energy levels to energy bands when we are talking about a solid. Still more on energy levels, but this time we are now talking about energy bands, and this happens in solids. And what are we saying? We are saying in a solid, the energy band diagram modifies to form what we call bands, and it is very, very important that you understand this. And we are saying millions of electrons exist or now belong to the first band in the solid, just the same as millions of electrons exist in the second, third, fourth, etc., etc. So we are now saying the energy levels are now transforming to energy bands. That's basically in a solid. Why this happens is in a solid, we are saying the electrons in a particular band are very, very close to each other, or electrons in a particular level, energy level, are very, very close to each other, resulting in one energy band. It will become clear if we proceed to the next slide, but we just wanted to see the transition from the discrete energy levels to discrete energy bands because of the millions of electrons in a particular orbital shell. Still on energy bands in solids, what are we saying? We are saying silicon and germanium are used to make most electronic devices like transistors and diodes. And we are saying germanium and silicon need the 4 electrons in their outermost shell, which is the valence shell, for them to be stable or to be unreactive, or for them not to take part in a chemical reaction. Because when the valence shell is containing 8 electrons, it is said to be full, and that atom can no longer take part in a chemical reaction. And we are saying when electrons are now 8 in the valence shell, they cannot move as there is nowhere else to go, especially in a crystal. So we are saying it is now stable. An atom is stable if it contains 8 electrons in its outermost shell. For electrical conduction, we are concerned about 2 bands, the conduction band and the valence band. The gap between the valence band and the conduction band is called the energy gap. It is electrons in the valence band that when they gain energy, they escape from the valence band into the conduction band. And once they are in the conduction band, they are referred to as free electrons. And these are the electrons that are responsible for electric current flow. So we are saying for an electron to escape from the valence band to the conduction band, it must acquire energy that is greater than the energy gap or the forbidden gap. And when electrons escape from the valence band to the conduction band, they are now known as free electrons. In other words, they are not attached to anyone, just as a man or a woman might at one time not be attached to anyone. So we are saying an electron in the conduction band is least attracted to the nucleus of a particular atom. So it does not belong to any particular atom. We are now going to look at the energy band illustration for conductors, insulators, and semiconductors. We are starting with conductors, and we know that metals are very good conductors. Then we go to insulators, and we'll finish with semiconductors. We said in solids, instead of energy levels, we now have energy bands. So we have got the valence band for all the materials, for conductors, insulators, and semiconductors. And we also have the conduction bands for the 3 materials. We are not concerned about the first, second bands. Why? Because I think we've agreed that it is the valence band that determines the characteristics or the behavior of materials. It is only electrons. It is only free electrons that contributes to electric current or to electricity flow. And when electrons escape from the valence band into the conduction band, they are now known as free electrons. Hence, this is a very, very important band. And as you can see, in conductors, there is an overlap between the valence band and the conduction band. There is no distinction. Hence, as you can see, even at room temperature, we already have got valence electrons that have escaped into the conduction bands. This is a very important characteristic that identified metals as good conductors. Or this is important for the definition of a conductor, in that it is a substance that allows electric current to flow through it easily. Why? Because it has got a lot of free electrons. Then an insulator, as you can see, we've got what we call the energy gap, and you need 5 electron volts or more for an electron to escape from the valence band to the conduction band. This means that if you have got less than 5 electron volts, then the insulator will not conduct. This is very important for you to, it is very important for you to understand that this is the reason why, unless an insulator breaks down, it will not conduct. So an insulator is a material that does not allow electricity to pass through it easily. Why easily? Because you need at least 5 electron volts for an electron to escape from the valence band to the conduction band. And it is only then, when we have got so much free electrons, that an insulator is able to conduct. So to a certain extent, if it goes into breakdown, an insulator will conduct. Please take note. Then, for a semiconductor, which is our material of interest in electronics, because electronics is basically the start of semiconductor materials, the energy gap or the forbidden gap is narrow when compared to the valence band, in that you need at least 1 electron volt for a semiconductor to conduct, or 4 electrons to escape from the valence band into the conduction band. So, a semiconductor is, from the word semi, its conductivity is between that of a insulator and a conductor. As you can see, even it is depicted by the narrow forbidden gap. The last slide in this presentation, we are looking at the properties of semiconductors. In other words, we are looking at the properties of germanium and silicon atoms. And the first one is the resistivity of a semiconductor is less than that of an insulator, but more than that of a conductor. I think I have exhausted that point. Then a semiconductor is almost filled the valence band and nearly empty conduction band, with a small energy gap separating the two. We've seen that when we looked at the energy band, the differences between a conductor, insulator, and semiconductor, and we saw that very important point. Then a semiconductor has got negative temperature coefficient, which means that if we increase the temperature, we increase its conduction, because electrons will gain energy and jump from the valence band to the conduction band. Then the other point, when a suitable metallic impurity, we are talking about doping, that if we add some external atoms into a silicon or germanium crystal, we are injecting some charge carriers like electrons and holes. Hence, its current conducting ability is improved. Then a semiconductor is formed by covalent bonds. We know that a silicon or germanium atom having 4 electrons in the valence shell, it can only be stable if it shares with 4 nearby atoms. Hence, that type of bonding is called covalent bonding. Then the last one is a semiconductor crystal structure arranged in an orderly manner. Guys, I hope you have enjoyed this one. In the next video presentation, we'll be looking at intrinsic and extrinsic semiconductors. But otherwise, enjoy yourself.